Does everyone have a lecture worksheet? Does everyone have a lecture worksheet? Yes, yes, yes. OK.
Desaus, é.
All right, all right. OK, let's get the lecture started. Come on, guys. Oh, thanks. All right. So if you just came in, we have the lecture worksheet at the back of the class. If it's ran out there, we still have some couple left at the front. So make sure you grab a lecture sheet, and we will get the lecture started. How is everyone doing after the midterm? What's the vibe? Going all right? OK, sounds good. So today in the lecture, we're going to talk about the timers. Hope you guys still remember. That's the topic we stopped talking about one lecture before two lectures before the midterm. So today we're going to first finish up the PWM signals, and then we will move on to the virtual timer. Before that, a few announcements. First, we have the homework 4 up and running, and then it will be due on the Saturday, so one later than the normal Friday deadline, so that you have some extra time. For the exam 1, we're currently still grading it. This is the distribution. I think it looks pretty OK. What's the axis? Oh, that's a good question. So we haven't finished grading everything. We have 14 points left, and on the axis here, this is 90, this is 80, this is 70. So we will anticipate to have a mean to be around like 75-ish. So, and OK, let it sink in. Any questions? I hear a lot of discussion. Any questions? What? Do you have questions? Oh, so this is 100, this is 90, this is 80, this is 70, if I remember it correctly. And we have 14 points left to the grade. So if you think you did all right on the drawings, the problem that we went through multiple times during the class, you'll be good. If you did poorly on that one, this is your score. So, any questions regarding the? We will release the score tomorrow. We will hopefully finish grading that tonight. Yep. Yeah, this is not the total score. Imagine this is to be capped at, 80, 86. So, yeah. And in case you didn't notice, the exam was out of 100. So, for those who are going to go beyond this 100 points, sucks to be you. Those points are not going to be counted. So, yeah. Any other questions?
When will the grades be released?
Hopefully tomorrow. Hopefully we will finish the remaining grading tonight. So we have, but that grading does take some time because it's the drawing, and you guys probably remember, it's not the most clean drawings you guys draw on the exam. So that might take some time. We did release the solution on the class website. So if you want to, just check it out, feel free. And some of these solutions, we only provide like one possible solution or two. It's possible that we have like multiple solutions, more than that, as long as you have your assumptions and any statements written in your answer. You can still get full points or get some partial points for that. Any other questions regarding the exam one? OK, perfect. That was shorter than I expected. So next, we're going to move on to some of the interesting part of this class. The pace of this class is going to be a little bit faster from this point. First, we have the final project. It's going to be on the horizon. And the first part to do that is to form some of your individual ideation slides. And then for that, will be due on this Thursday. We have on the class website posted a OK, where is it? OK. So if you click on here, we have some document here to just help you guide through what a ideation slides could look like. We included some examples. Doesn't have to be super fancy. Some drawings and a few bullet points will do. But do remember to put a star at the project that you like the most. And this will be due just before the team formation event. Another thing is we have also a handout. I think it's this one. So this document also linking that ideation basically explained, for the final project, what are expected from you and from the team, how we calculate the scores and everything. It's a pretty long document, but it's quite detailed. If you have any questions, feel free to post on the Piazza. We're going to enforce the team of at least 4 people for this class for this semester. So 4 to 5 people will be like a standard team size. And for the team formation event, it's going to be this Friday, same time as the exam, and at one of the exam room as well, the Dow 1013. And we will have pizza served during the event so that it's a nice and cozy vibe for you guys to form your project team. So by default, everyone is expected to be there. So during the event, everyone would just go on stage, spend like 30 seconds to 1 minute to just introduce yourself to the class, who you are, what you studied on, and what are the interest projects or interest directions you would like to go with the final project. And then after we do that, we hope we can have like a natural environment for people to just, maybe this group of people interested in like robotics related, this group of people interested in like, I don't know, camera-based or something like that, so that naturally we can form the groups based on the interest. If you already have a group assignment, please still try to show up unless it's you have like a explicit email from us to make the exception. Otherwise, please still do show up to get to know your classmate, as well as I know a lot of folks, the team they formed is only like 3 people or so. So you will need to at least find one more person for your 3 people group. Any questions regarding the team formation? All good? OK, so while we're at it, let's actually maybe go through the project description a little bit. So basically, the important part is how we're going to do the grading, right? Or what's being expected of your of your project. You can think about them as, based on the amount of team members, you will have amount of the components you work on, maybe +1. So the components we define as like either a peripherals that you attach to your system or a additional communication protocols, which we haven't talked too much in the lecture yet, but we will do in later, like I2Cs, SPIs, Wi-Fi or Bluetooth, etc. These will all be count. And the if you look here, the maximum value of the highest value you can possibly get for the final projects, 107, and that score we will not cap at 100. So if you actually overflow on this, you will compensate on your other part of the class. So if you did a little bit poorly on the exam, this is the points you can make up. On the good, like a decent project, we'll get about like 88% out of the 100. So that would be considered like a pretty good project. The things that are a little bit harder is the difficulty components as well as the like an integration score. So those two. And how do we calculate that is, if we go down. Yeah, the difficulty, we have some examples, like what components considered as good, like easy, mild, difficult, as well as like very difficult. If you have, okay. And this is basically how we're going to calculate the values. We capped it at 40 for this, and then but feel free to exceed the difficulty score. Regarding to the group size, we have a weight factor. We get rid of the 2 and 3 group options because of the class size and the limited lab space we have. For the group of 5 and 4. The difficulty score basically will be multiplied by this factor, 0.7 or 0.6. And you should all end up with, roughly similar, like the complexity or difficulty scores. Another thing is, we weighted more on the system integration because now that, maybe getting system integration basically means that you have all the sensor modules, all the peripherals and communications work together as a full prototype. And the difficulty usually refers to how hard it is for each of the individual components to work. Any questions regarding difficulty and integration? I think those are probably the two main part of the final project. Okay. And what else? Oh yeah, we have a Google Doc / Google Sheet that keep tracking of the components we already have in the class. So we don't like set a hard budget for how much you're supposed to spend on your, or not supposed, how much you're allowed to spend on your final project, because a lot of those components are likely going to be available already. But if you do have something like very customized, very special you want to use, let us know, let James know as well, so that we can figure out either we have something similar you can use, or we need to make the purchase for your final project. But for those who are thinking about that, please make sure you contact us earlier, or like you make the decision earlier, so that we have enough time for the parts to be processed and then arrive. Yeah. And for those who wants to maybe make a PCB, this is also, make sure you contact us early enough so that you can actually have it in the end, instead of have like a, hard-wired breadboard or protoboard. But basically, we are pretty flexible with the ideas and the final projects. And for the ideation stage, feel free to just think bold and present however that interests you. We will meet with you on a more regular basis, the teaching team, so that we will make sure your project in the end fits the scope of the class, as well as it's fits all the requirements, and it's not too ambitious that you can't finish, or it's too easy or too straightforward that you just get it done 1 week or something. All right, any questions regarding the final project, the team formation, or any of these? Okay, perfect. So I guess I will expect to see you on Friday for the team formation. For today's lecture, we're gonna first, finish up or continuing on the timers that we talked about last Tuesday, and then the virtual timers. We're probably not gonna start on the communication buses, so that we just have the lecture more cleanly defined. So probably just the top two. First, a little bit recap. We have the, on like a timers perspective, we have the hardware clock that's being filtered by the clock drivers and like a clean signal coming in, and then first go through a prescaler to basically slow it down to a more appropriate clock for the system. And that goes to the timer counter. The counter basically does one thing, but it does it really good, which is counting up or counting down or counting up and down. And then we have an additional ARR. It's like a auto reload register. So whenever it hits where it's supposed to count, and then you go back to the the 0 or the maximum value. Depends on you have it set to be counting up or counting down. And we have the CCR registers, the compare and capture registers. For the capture mode, usually it's for the for some input signal coming in. For example, if we have like a GPIO signal, that flag is being up, and then the capture register will basically log that time. And then, by logging basically means take whatever in the time counter right now, so to save as a timestamp. And that usually triggers the ISR for the core. So if the core, or whether the core responds to this immediately or wait for sometimes or never respond, it's depend on your program or depend on the core's behavior. But there will be usually an interrupt being flagged there, so that if the core decided to check on this signal, it will know exactly when that's happened, rather than if it goes all the way to check the time counter, which means you will getting the time of when the core actually check on the interrupt. Then that might cause some extra delays. So this will be in the capture mode what the CCR register is doing. And we also have the compare mode. Basically, on the compare mode, the CCR register, the compare will basically store a value there, and whenever the time counter reach that value, it will triggers a ISR, a time interrupt signal, and that will be used for. Depends on how you implemented it, but it can be used for like periodic interrupts commands, or in our case, the PWM signals, a very commonly used case. And we talked about we started to talk about the PWM signals. So the PWM signal typically have these two modes. The mode one is called low chew. Basically means that the timer's output will be, the signal output will be high if the counter's value is less than the CCR, the compare register. And it will be low if the counter is greater or equal to the compare register. So it could give you like a example here. If we have the CCR set to be 3 and the counter to just counting up in like an up counting mode with the ARR auto reload register set at 6. So that will be where the cutoff line is, and the actual output signal will be something like this. So if it's lower or equal to the number 3, then the signal will be high. If it's higher than that, the signal will be low. So this will be the PWM signal that's being generated. And to calculate the duty cycle on this one, it's typically just use the CCR value and then divide it by the ARR plus 1. The reason we do plus 1 here is so that we make sure the programmer doesn't make any mistake on the divider 0 situation. And make sure you notice what's the number to put on the top. Is it the CCR or is it the ARR minus CCR? That would depend on the mode, basically which one is. In this case, it's CCR value, the compare register value, because it's high if the counter value is less than that CCR register value. To calculate the period, again, we have the 1 plus the AR and then times the clock period. That will give you how long each period of this PWM single is. Any questions on this? So the period stands for the entire length of this period of the counter, and then the duty cycle stands for the percentage of ones inside of this period, basically. Any questions regarding the duty cycle and the period? Yeah. Yes.
Can I ask, like the CCR register, does it either do compare or capture, or does it do both?
It's usually either compare or capture, but you can also disable it, just not using it. Also, we have multiple CCR registers, which will show. Okay, can you pass it down to the? I think we might still have some left at the back of the lecture hall. Do everyone have the worksheet? Okay, I have one last one. I printed out 150. We only have 143 students. Okay, so this is the PWM mode 1, basically the low chew. Do anyone see any wandering lecture worksheet somewhere in the classroom? Okay. All right. Please only pick up for yourself. Okay. This is the mode 1. We also have, as you probably expected, the mode 2, which is the high chew. Basically, it's pretty straightforward. If it's the signal will be low or logic 0 if the counter's value is less than the CCR. And it will be high if the counter's value is larger or equal to the CCR value. And again, here with the AR to be 6 and the CCR, the compare and capture register to be 3, this will the output signal be look like. So it's pretty much flipped compared to the previous one. The RCR value here, by the way, the 0 basically means that this is the periodically happening signal to the end of time. If you give 1 or 2 other values, that means how many times this period is going to happen. Any questions regarding this? And like we said, when you calculate this, it will be 1 minus the CCR, and the periods will be the same as before. I think, yeah.
Why does the output toggle at the start of the CCR equals 3?
Yeah, why does it toggle? Okay, that's a very good question. So let's not get bugged at whether it's tagged at the beginning or the end. It's just one cycle, and chances are you have more than 10 as the AR values. This will solve this issue. So for example, if you want to say if you want to have like an exact 4/7, right? One implementation is you can just set the CCR to 6 so that you have a maximum have like a 1/7 missteps in between, right? But you can also set it to be 69 so that in the end it will be 70. So it would be 39/40. Then you have 1/70 percentage of off shift in the system. And you can even set it to 699, and then you have 1/700 of the misstep in between. So it's a digital system. You will learn later at the analog to digital converter, digital to analog converter, that there are some small, maybe one clock cycle potential missteps, but this you don't have to worry too much about it. Just use that value and then divide it by AR plus 1. The plus 1 is the important thing here. Just, take the CCR value. Any other questions? Okay, so for this is also the upcounting mode for the PWM. And just to give you one more example, if you set the CCR to be 5, that basically and again in the high true mode, and this will be the signal you have. And this will be how you calculate the duty cycle and the period. And basically, each of these, if you can see my cursor, from here to here will be like one cycle or one period of time. Yep. And we have the PWM signals in different counting mode. We have the up counting, down counting, and we also have the center aligned, basically up counting and down counting. This is so that you can essentially have double the amount of resolution, if you may think, for the same bit of the counter register you have. And in this case, the let's say if it's still in the mode 2, the high true, the duty cycle and the periods calculation might slightly be different. For the duty cycle ones, it looks pretty similar, but for the periods, just make sure you have the number 2 in the front, so that the time is essentially for each period is essentially doubled. And if you really want to know, you can just draw it out. And for the 3, why is it at the beginning or at the end of that cycle? It usually depends on whether it's greater or equals, like where that equals was aligned at. And if we have the CCR to be 1 in this case, and then this will be the end signal that's been generated, a lot of highs, and then you have the duty cycle and the period calculation here, the same formula. Any questions on this center counting mode? Okay, cool. So as we said before, one counter can be connected to multiple CCR registers, and each of them can be individually set to be either capture mode or the compare mode. And that gives you a lot of freedoms of just using one timer and the counter, and to do a lot of these like operations for input and output. And with all these things, you can also do a little bit like some fancy things, or to make sure if we do it like the PWM signal, some of the cool things we could do is, for example, in this case, we can have all the signals to be left edge aligned. So in this case, we have 2 of the registers. One have the CCR to be 6, and one have the CCR to be 3, so that whenever it reaches that signal, the shift happens, so that on the rising edge of these 2 PWM signals, they're synced in this case. And similarly, you can also have it to be right aligned, as well as center aligned. So you might wonder, why do you need to do that? That depends on which type of peripherals you control. For example, if you are using the PWM signals to control multiple servers or motors, you want them to be very precise, and then they don't just individually drive stuff, they work together. So you want to make sure that they start at exactly the same time, or stop at exactly the same time, or in the middle they aligned. So some of these, so that in the timing, these components can work together. And during like a typical PWM signal generation, as you would, I think, soon implementing in the labs as well as your final project, it's more common to change essentially the CCR values to change the duty cycle. So meaning change how many percent of the highs goes into, or how many percent of the power goes into your peripherals. Any guesses? Oh, yeah.
Is this like completely separate from the like high true mode, or is this an extension of it?
Oh, it's they all work together. Like you can also set one of them to be high true, one of them to be low true, to do like some even fancier alignment. For example, if one is high true, one is low true, then I guess this one, so that the center of the high signal from the top will match the center of the low signal on the bottom. You can set each of this individually. And for the PWM signal, any guesses on why people usually change the duty cycle rather than change the periods?
Because if we change the AR, the PWM frequency will change.
Yes, the PWM frequency, like the whole period will change. And anything else? Or like what kind of result would that cause? So there will be a few results that cause. First, as we said, each of these counters, they're connected to multiple CRRs. So chances are you have multiple of these signals, possibly depending on the same counter and the AR register here. So if you just set AR values, that might affect the other PWM signals. And then another thing is that it's just so much easier to change one register's value rather than if you go through there, it changes a whole bunch of things. If you just think about like the cost. So normally for the PWM signal, it's you set the AR value at the beginning, and then most of the time you don't change it that often. However, if you do want to change it, then the STM also provides you a way to do that. And it gives you freedoms of whether you want to change that immediately or you want to wait until that cycle has finished to change. This is done through this auto reload preload enable bit. This is 1 bit register. This is 1 bit that's used to control whether, like after you reset the AR value, whether you want that changes to happen immediately, meaning next clock cycle, or if you wanted to change it after the whole counting process has been finished. Meaning if we have like the AR set to be 6 and the up counting mode, if we have this command trigger at the counter at 2, it will wait until that 6 and go back to 0 and then change the AR value. So in that case, the PWM signals that's been generated, the new PWM signal that's been generated will be in sync with the previous PWM signal. And if we do it immediately, then it's going to be an asynchronized setup. But depends on how urgent you think this switch is, and depends on your program design. You have the options to either change it immediately or change it after the entire circle to be finished. Any questions regarding this? Okay, perfect. Then I have a question for you. So let's look at the lecture worksheet. So this is basically asking you to build this PWM signals that let's say it's the mode 2, and then we will need to be generating like a duty cycle of 10% and a period time of 10 milliseconds. And assuming the input clock is at 16 megahertz. It would be, multiple answers will be expected as long as you can justify the number you selected. So, cool. Let's spend maybe 5 minutes or so on this, and then we can look at the problem together.
What the hell do we do for our project? Okay, I think. Cool. Pretty hard. No? Would be the host.
All right, let's share some wisdoms. So this is the signal we're trying to get. The period of 10 milliseconds and the duty cycle to be 10%, which means 1 millisecond. And to, the calculation formula here for the prescaler is just the clock in divided by the prescaler number plus 1. So who wants to share their choice of prescaler? What did you choose for your prescaler value? And what's the output after that prescaler? Anyone? Yes?
15 and then 1 megahertz after that?
And can you explain a little bit why you chose this out of all these numbers?
Because the input clock is 16 megahertz. You want to divide it by 16 total to get it to 1 megahertz, which correlates to 1 millisecond. So that'd be 15 prescaler input.
I think that's less than 1 millisecond, right? But I think the answer is actually pretty, I think nevertheless, the number you chose is pretty decent for this case. Anyone else have other numbers they want to share for the prescaler? Did anyone choose more than, say, 1600 for the prescaler? No one? Oh, wow. OK. Yeah, nice. I think, nevertheless, how you calculated it, the 16 is, or like 15 is a pretty decent number. And typically, we do not want the prescaler to be too large. The reason for that is if you remember from the previous slides, maybe one more. So after the prescaler comes in, after the clock goes to prescaler, that clock will be used for the time for the counter ARR, and this whole thing was actually connected to a bunch of CCR registers. So meaning that this signal is not only just for this one PWM signal. And chances are some of these CCR registers, capture and compare registers, some of them might be set to capture mode. So you do not want that to take just too long to be responsive. So generally, we want the prescaler to be like a decently, basically not too big. There's no exact number you should aim for, but typically if you have like a couple megahertz after the prescaler, or have a few 100K hertz after the prescaler, that's all like reasonable numbers. So let's say we have the 15 as the prescaler number, and we nicely cut down the clock to 1 megahertz. What would the ARR and the CCR be? Does anyone else use 15 for the prescaler? Yes.
I used it, so I got that then the ARR, I got 5,000.
5,000, and the reason for that is?
Like we said, period is 2 times ARR times clock period, so.
Yes, and the reason for the 2 is because we're doing this up-counting and down-counting mode. And for the, what did you choose for the CCR again?
So the prescaler was 15, then I got that the ARR was 5,000, and then I got CCR as 40,000.
Yes, exactly. So this is also happens to be our configurations. The prescaler to be 15, nicely cut it down to 1 megahertz. You can do a few more if you want, or a few less for the prescaler. And the AR to be 5,000 and the CCR to be 4,500. And I hope this example also, yes, question?
When we're calculating the prescaler, why are we doing 16 divided by 1 plus 15 and then it's determining if the prescaler is 15? Where is the 1 plus 15?
The 1 plus is hard-coded in the hardware. So basically to make sure that no programmer is too smart and put a 0 for the prescaler, just to be safe. Any other questions? I hope this example also give you a little bit ease on the fact that when you do the counting, this line where it draws can go a little bit either way. It doesn't matter that much if say this when it's 3, it's cut off on the positive edge of 3 or the negative edge of 3. Chances are you will have like a pretty decent like AR and CCR value, so that if you say we have like 5,000 here in this configuration, which is kind of typical, or even just have like 1,000 as they are, then that it's like 0.1% of a little bit misaligned. So it doesn't matter that much. And when you do the calculation on the CCR divided by AR, is it CCR plus 1 divided by AR, or is this minus 1 divided by AR? It doesn't matter that much when we have like the number of these to be like in magnitude higher than the percentage you are looking for, which is also pretty commonly configured, the way to configure. I think I saw a question here. Was it? Oh, okay, cool. Any other questions regarding this worksheet question? Cool. So another fun question to just calculate here. Let's say we have an input clock of 100 megahertz. And what's the maximum timeout period for 16-bit a timer, 32-bit timer, and then 64-bit timer? Let's maybe work together for, I don't know, 2 minutes, and then we can all share the answers. All right, anyone calculate this so far? What's the 16-bit timer gonna give for like a maximum timeout period? Anyone? You can just shout out answer if you have it. Does anyone have access to a calculator? Maybe computer? I think someone, I think I calculated last year, so it's around like sub-millisecond, sub 1 millisecond. I think more exact would be 0.655 millisecond. Is that the number you get? Okay, good. Yeah, you can say that out loud, by the way. For the 32-bit timer, what's the maximum time you guys got? 40 second-ish? Is that what everyone gets? 42.9 seconds? Okay, it's just, okay. And for the 64-bit, it would be like, about 6,000 years. We can probably use that to count the time for species to exist or something. Cool. So yeah. What's the timeout period actually does? It's basically if you, it's the counter you can, the counter you use the maximum length of the period you can have for a signal you want to generate. Any other questions? Yeah. Oh, good question. I actually didn't know if this was done by count up and count down or just count up. But roughly the same. 6,000 years versus 12,000 years, virtually identical to us. Anyway, so that would be for the timers part, and then from like a hardware perspective, and then we will talk about the virtual timers, basically another layer built on top of these hardware. The previous timers are all considered as hardware timers, by the way, because they're all connected to an actual physical clock that's go up and down, up and down. And in this, we're going to go a little bit more abstract. So, and a reminder of the anatomy of the timer system. So we have talked about the downs, everything down there, and then when we go one level up, there's this time abstraction and virtualization bit. And why do we need the virtual timers? You might be thinking. It's usually because for the computers, one job it needs to do and do really well is just keep counting and keep the time, right? But how many timers will be enough for a complicated exam, like a complicated program you're writing, or even if you have like multi-cores, they're all doing their own things. It's probably not feasible to have like one timer or like one hardware timers that connects to everything, or even if they have multiple CCR register, right? It's just not going to be enough as the program became more and more complicated. And so what we're going to do about it, we're going to probably handle in the software, as you might tell from the title here, virtual timer. And let's do like a quick brainstorm on like how would you implement this? Mainly if you have one hardware timer with the counting and all that, and you have multiple events that's going to happen at various different times. Some of them happen once, some of them happen periodically. How do you use that one timer to create a bunch of virtual timers to keep track of everything? Let's discuss maybe for like 2 minutes, and then we can share some thoughts. All right. Anyone wants to share how would you implement this in software based on one hardware timers you have, with the counters, counter registers and everything? How would you implement this? One timer times null. Anyone wants to share? I think I hear a lot of discussions, so some of you guys must have some idea. Yes?
I guess you could have one very, very fast timer that like interrupts every certain, like at a level of granularity that's fast enough to implement all your other virtual timers.
So you
and
have,
then you would implement whatever logic is needed in software to ignore some of those interrupts and only consider the ones that are relevant to you at certain like divisions of that really fast timer.
so like essentially we create like a super fast MVIC type of thing, but in virtually, and then just connect like a very fast clock to it, and then just periodically check all the aligned event. And whenever some of them go off, and then we executed that, and then keep that tracking, right?
Something like that. I was thinking like a systic type of timer.
Systic, yes, yeah. Yeah, I think that will work actually. That will work. It might be a little bit too costly, but it will work actually. Yeah. So if we say we have like some embedded system that all the event is expecting are like pretty slow, for example, in the magnitude of second, or every second you expect something to happen, and then you can connect through like a reasonable clock, and then you should be able to track all of these with that configuration. Any other thoughts on how would we do this? Okay, so how they decided to do this is that it's pretty straightforward. Let's say we have a bunch of events along the way. They all happen at different time. Say we have these 4 events, or even imagine there's like 20 more. And then this supposed to happen at 10, t equals 10, 13, 20, 43. Oh, first we do like a sort, sort on the time where each of these events is supposed to happen. And we will make them, we will set the timer, the counter's value, to be just the value that needs to be go off for the first event. So for this, we will set like a compare to be 10. So 1, and then the time start to click, and then when it reaches 10, it happens. And then all these remaining events time got updated by the amount of time that's being passed. So the 13 becomes 3, 20 becomes 10, etc. And then we set that the compare value, to set the timer's value to be 3. The first value that's gonna happen next. And then we do that, and then just keep it going until the end. Does this look reasonable to you guys? Or like a reasonable configuration? Any questions? Cool. So let's go through like a more detailed example for this. So let's say, to show you how exactly this works. If you look at the top right, that's the hardware timer we have. We have like a counter value inside of that to be set every time when there is a event happens, for example. And we have these bunch of programs that's trying to be executed. Setup time is basically means what's the time it needs to be triggered. And if it's at 3 or at 5, that means it happen at time t equals 3 and t equals 5, and that happens once. And if we have like a number d in front of the delta, that basically means it happens every 2 seconds or every 7 seconds. So first we will just have them all be together into like a virtual event queue. Imagine you have like a bunch of like BL instructions that will jump to each of these handlers and do something, right? So first, we just store them from the top to bottom. We have the time 3, so we set that event time to be 3. And the delta basically means whether it's a repeated event or not. And then immediately we'll update the hardware timers count to 3. And then with more things going, the 5 doesn't change that timer because it's larger than number 3. It's not the first event that's going to go off. So the hardware timer there, the count is still going to be saved as 3. And then later on, we have the program 2 coming. It's a time at 2, and it's a delta. So we would do a resort and then update that count number in the hardware timer to be 2. And we have 7, and then it's larger than 5, so we just keep it there. And the timer 4, we do another resort and sort it back. The reason that we do not list like the like 2 everywhere in this list is so that it will be added or repopulated every time that event is being executed. So it's you can think of these like periodic programs. Yes.
Just to clarify, the head pointer points to the closest deadline.
Yeah, the count time is pointing to like currently on the event list what's the first event that's going to happen.
Okay.
Yeah. So the smallest number. And then we have the time start to ticking, and 2, 1, whenever it reaches 0, as we have in the timer configuration, there is an event ISR being triggered, and that executed the first one that in the list. And first, it will figure out the source, and we know it is this program, and we will then remove the head of this event from the list and update times. And then insert the new event. If this is like a duplicated event, in this case it is. So we, oh, by the way, for the update time, we're meaning updating the time on everything inside of this virtual event list. So previously 3, 4, 5, 7, because there's 2, well, t equals 2 passed, so all of them minus 2 for when we're doing the update time. So it became 1, 2, 3, 5. And then we will insert new event. This is basically checking whether you need to reinsert another handler based on whether that is a recurring event or if there is some new event coming in. And then in this case, we actually do, and then we insert that as a 2. So sometimes you have some events that are supposed to happen at the same time, and when that happens, who is going to get executed first will be dependent on any thoughts? Will be dependent on their priority that we talked about before. So, but it's okay to list them just like this. It will be dependent on which one have the higher priority. But we insert the new times, set the new time, sorry, in the hardware timer. And in this case, because the earliest event it's going to happen is have a time 1, so we update that to 1 on the hardware timer. And then time ticks again, and then one cycle after, that event got triggered, and again we figure out the source. This is the program 1. We take it out. There is remove head and update time for everything else. So everything on the list going to be -1, and there is no new events going to be set because it's a one-time event. And we set the new timer, which is going to be 1, corresponding to the next 2. Any questions regarding this? So it basically just keep going on this. We have like a list of events that's going for this virtual timer. Yeah.
So does this have like small errors in how much time has passed? Because like let's say you pop it off the queue at time equals 1, and then you want to do something else at time equals 2, but some cycles have already passed before you set it.
That's a great question. We will actually touch a little bit later, but yeah, you're pointing out exactly what some limitations of the virtual timer. It's that it's not going to be as accurate as a hardware timer that we introduced it before. So typically, when you use this, it will be used for events that are less time sensitive, or the whole response time it can be like longer. For example, for human-facing events, if we miss a couple milliseconds, it's no big deal. But if it's for like some hardware, like GPIOs, then a few milliseconds actually have some. No, not GPIOs, for like PWM signals and stuff, a few milliseconds actually means a lot. So yeah, as we talked about before, it's possible that we have multiple events at the same time, and it will be determined by the priority level and which one gets to execute first. Yes?
You mentioned priority level. Does it mean like we can only have interrupts in this timer?
Not necessarily. So normally yes, but you could have other configurations. Just this priority, it can refer to the hardware priority bits that we mentioned before in the register. It can also refer to your code. Like how do you decide which one gonna go first? Like you can set, if multiple things happen, you have an if loop and then you do this first and then do that. Yes?
Is it ever possible that a event would be completely starved from actually running because you have maybe like 2 delta events that would be at a higher priority than it?
It will always have a higher priority than the other. It will be, okay, that's a good question. So we will have every time you will have some time passed, right? Even if you only have like every 1 cycle. So every time you added 1, and at some point, the higher priority event is gonna fall behind on one of the normal one.
Yeah.
And then when that happens, then that one got executed first, and then this.
Say that one more time.
So for example, if we have multiple of these event with the time 1 here, right? And say that orange one is higher priority, and they have another every 1 cycle gonna be here. So this one will have a 2, but it's a orange. It's the same event, right?
Yeah.
The system will execute that orange one first, and then do the blue one, because the next orange one, at some point, the next orange one is going to have a larger time number here. So when that happens, you first look at the time, and then look at the priority, only if they're the same time. If that makes sense.
Okay.
Yeah. Any other questions regarding this? And there are some caveats here, and there's some like side cases. So what if, say, we have an event coming in, but the system already be running for some time, right? What happens then? So what we will actually do is, let's take this one as example. Say the system has been executing for some time, and that's the Y, because you can tell by the count on the hardware timer is already 1, and then the next thing next thing on the list in the line, it has a time number of 3. That means like 2 time clock cycle, or 2 time has passed in this case, right, in the virtual timer. And then all of a sudden we have a new program coming in with a setup timer at delta 2, basically 2 seconds periodically, or two cycles periodically. So what's going to be, how are we going to do this? So basically, we will subtract the difference. Before inserting this to the list, we subtract the the time difference from all the elements in the list based on how much time has passed. So in this case, we will be subtract 2 because we have 1 in the counter, and then if we started at time 3 times minus 1 is 2. So we minus 2 on all the things on the list, which make them 1 and 3. And then after that, we insert the new event into the queue, which is going to make it like this. So let that go, and then the clock keep running, and then execute that first, and then this, and then add the periodic one back to the end of the list, and then just keep running. Any questions regarding? Yeah.
Did we subtract 2 because the new timer is D2, or because 2 seconds have elapsed in total?
Okay, that's a great question. So this D2 is a little bit confusing. It's because of the time is past 2 cycle. So previously, we will still subtract 2, even if that's like say D4 or D5. The 2 number comes from the fact that there are 2 cycles passed since the beginning of this last event. Because the top event on the list have a time of 3. That means that's the last time the list got updated, 3. And then we have the timer number counts to be 1. That means from the last time the list being updated, we have 2 cycles passed. So that's the number 2 that we use to subtract from the list. It's not the number 2 from the D2. Hope that's clear. We good? This seems to be like a reasonable way to handle this. Okay. And then we just keep updating the queue based on that. Any problem you can think of from using this virtual timer? I think some of our classmates actually mentioned one, and it's a pretty decent concern as well. Some other concerns, in this case, we only works for like the compare timer uses. You have to know, you can only use that to, like, whenever you have a time flag or variable there to check if the event hit that time, and then you can use that for timer. You can't really use for, like, say, capture, right? Because there's no trigger in this virtual timer for you to capture things as you go. We also, like, it might not be great for like very accurate timing, as one of the classmates mentioned, because the fact that some of the ISRs might take longer to be executed based on the priority level or based on that portion of code's priority, critical level. And it also will result in like slower interrupt ISR response time. But it might be okay for some of the use case as long as you treat them correctly. Like we said, if you chose it for some event that's less of a critical timing, or it have like some very wiggling rooms for the response time, or if you just have like a much faster hardware timers, so you are able to just lose some of these along the way. But basically, the virtual timer gives you a lot of controls over how you could use one hardware timer. Hardware timer meaning hardware timer, prescaler, like the counter, ARR, auto reload register, the CCR, compare and capture register. All these one timer. The way you can use one timer to control a bunch of, or keep track of bunch of events. Any questions regarding? Yeah.
So just to clarify, does it always use a decrementing timer to make this work?
For the virtual timer, in most of that, yes, you use the decrementing. Yeah. Any other questions? All right, cool. So this will mark the end of this lecture. If you have any questions, feel free to come to me, and we will try to release the exam 1 tomorrow. All right. Thank you.
Please leave your worksheet. Please leave your worksheet. Please leave your worksheet. Please leave your worksheet.